Hi everyone, my name is Min Huang and I'll be presenting our work. The title is AI-driven methods for eliminating harmonic oscillation in inverter-connected system. We'll make a review and propose solutions. This work is part of the collaborated effort between me and two of my supervisors, Dr. Khương and Radomir from RMIT University and VSB Technical University of Ostrava. So here's the content of this presentation. First, we'll go through the motivation of our work. Then we'll make a little bit of literature review, and then we'll compare some existing methods, propose methods for the future work on harmonic oscillation mitigation, and finally we'll make a conclusion and some reference to it. So the first section we'll be talking about the motivation on why harmonic oscillation matters. So to understand why this topic is important, let's consider what is happening right now in the modern power system world. Traditionally, the electric grid, they were dominated by rotating machine, slow electromechanical dynamics, or well-known harmonics characteristics. But right now, the grid has been transitioning to like distributed generation, power electronic converters, or faster electromagnetic behavior. So instead of stable sinusoidal source, we'll now have some inverters. So inverters mean with switching action inherently to generate the harmonics. But this is right now causing some problems. So why is it a problem? Because the harmonics will cause a lot of distorted waveforms, some heatings in cables, some renaissance phenomena, reduce the lifespans of the equipment, and even some instability of the microgrid. So the challenge become even more severe when many of the inverter-based resources interact and they create more dynamic time-varying harmonic patterns. So it leads to some new class issues like converter-driven stability, passive or active, and renaissance stability. And these problems cannot be solved by traditional fixed method harmonic filter. So we'll have to propose an AI-driven method detection approach to necessarily identify and mitigate those dominant harmonic frequency in real time. First, we'll go through a literature review of some of the first conventional methods. They are limited for dynamic grids, things like Fourier transform based method, wavelet transform based method, and adaptive filtering based method. So the first one will be about the Fourier transform methods, especially the fast Fourier transform. So what we know about fast Fourier transform or FFT is very simple and computationally efficient because it just decomposes a waveform into like sine wave or different frequencies, like breaking down a music chord into individual notes. So logically, they are extremely accurate, but the limitation of it is that it assumes single stationary, meaning that it assumes the signal does not change within the analysis window. In real power system, harmonic appears to only have a few cycles. The inverter switching creates some bursts, and grid currents will fluctuate a lot with load of changes. So if the signal changes inside the FFT window, it will smear the energy across multiple frequencies, so leading to wrong frequency estimation, harmonic leakage, and high measurement errors. So some of the study shows that the maximum error it can reach is 5.7 voltage, which is unacceptable for inverter control. The second one, we're talking about the wavelet transform based methods. So wavelet transform fix the FFT biggest problem by letting us zoom into the signal both in the time and the frequency. So if the FFT is like looking at the entire signal from far away, then the wavelet will be looking through like a magnifying glass to zoom into a specific location. So it works by using a sliding window and slide wavelet function across the signal and look at the similarities. So it will provide us with a multi-resolutional analysis in both time and frequency domains. We call it the DWT, discrete wavelet transform. It can decompose the signal into approximation of low frequency and the detail in high frequency. The strength of it is that it is excellent for detecting dynamic and transient harmonics. It can also localize where in time a harmonic may occur and very suitable for voltage swell or harmonic events. The limitation of it is that it will suffer from very high computational cost and implementation complexity. So it's very challenging for real-time use, especially at high sampling rates. The third one will be about adaptive filtering method. We have two of them, the LMS, least mean square, and the RLS, recursive least square. LMS, just like adjusting the steering wheel slightly at each moment to update the filter coefficient gradually based on the errors. And in this case, we use least mean square error. It's very simple, low computational cost, works well with like stationary and slowly varying harmonics. But the weakness is that it converges very slowly and may sensitive to noise. So in faster dynamic inverter system, LMS may not be able to keep up. Similarly for RLS, it requires higher computational resources. It solved the problem by considering the past error more heavily, so it requires more computational resources, and specifically it has a lot of metric computation and inversion inside, so they are not yet ideal for like low cost hardware. But we can see that since they consider past error, they are promising, but right now they are limited by the hardware constraint, which is why we are moving to the second part of the literature review when we talk about the AI-based method. Since AI is becoming more and more popular and useful nowadays, we'll talk about machine learning, deep learning, and hybrid AI methods. So for machine learning methods, we can achieve very high accuracy in detection because we are learning pattern directly from the data rather than relying on the formula or transformation. So some of the machine learning methods that we have are, for example, SVM, support vector machine classifier, work by finding the boundary between different harmonic classes, and it works very well with small data set and has very good generalization, and it also performs well with transform features like the WT coefficient. It can reach up to like 94.95% accuracy in classifier, um, but it will need some good feature extraction stage and cannot learn automatically from raw data, so it's accurate but not fully automatic. The second one is KNN classifier, create and classify the new signal by comparing it to the nearest store patterns or neighbor. It can achieve up to 99.89% accuracy when used with some very specific feature selection. So the weakness is that you need some very well pre-processing input and has very slow inference for larger data set. So technically, KNN is very accurate but very expensive for modern embedded system. We also had extra thing like extreme learning machine. It randomly initialize hidden neurons and only train the output layer, so they are like 10 times faster than other conventional neural network stuff. Very good at fine tuning, but the weakness is that it has a random weight initialization, so they can be unstable, and they're not very ideal for longer sequential patterns. So the ML methods, so very good promise, but still relies heavily on good feature extraction. So deep learning methods uh, go in and improve us by automatically extract the feature and learn from the raw waveform patterns. We have the convolutional neural networks, which extract the spatial features for the motivation. So if you convert the signal into spectrogram or use like statistical feature, the CNN filter will detect meaningful shape like harmonic cluster, change in amplitude or waveform distortion, and automatically learn the important features and very robust to the noise. So it can achieve a THD value as low as like 0.93% in simulation, which outperform classical filters. The second one will be GRO, RNN, LSTM based methods, and they are built on hybrid shunt active filter system. We call it a SHAP, and they learn the time dependency over time since harmonic evolves over time. So we'll need some sequential models, and this SHAP machine significantly reduce the THD um, from like 58.7% to 2.1%, of huge improvement right there. And for modern system, we also combine multiple techniques to improve the precision of them. We call them hybrid AI methods. For example, we combine fast Fourier transform with adaptive neural network to achieve a maximum error, reduce the error to 0.03 voltage in estimation, which is much smaller than other. We also have other techniques like combining CNN with bidirectional LSTM and attention mechanism to learn both the spatial and temporal patterns. We also have the ANFIS, which is the neural fuzzy combination to reduce the THD significantly. So these hybrid methods will exploit the wavelets more precisely for especially spectral localization. The neural network, for example, will learn the nonlinearity of it, and and attention mechanism, for example, will focus on important harmonic events. So they achieve extremely high accuracy in research right now. So in this third section here, we'll go through some of the comparison of some of the existing methods. We can see that the uh, methods like fast Fourier transform, they use FFT for sequence frequency domains analysis. They are simple, widely used, but fails for non-stationary harmonics. Wavelet transform, very good for transient, but very computationally heavy. LMS and ROS, they are adaptive. They can do real-time processing, but they are very slow in conversion and have some hardware constraint. ML, deep learning methods, learns the pattern adaptively, and it can be adaptable to varying condition. It requires very large data set and high training complexity. And finally, we have the hybrid method. They have best accuracy and highest complexity right now. And for us, we will in this section we'll propose what we call a new hybrid method called the waveless neural network, which combine the wavelet transform with neural network for adaptive harmonic filtering. It will have very high accuracy, adaptive learning, and very effective for dynamic grids. But we also know that since this is a hybrid method, it will be computationally intensive and will need a lot of optimization for real-time use. So in this proposed method, we'll propose like time frequency analysis based neural network, especially for three-phase signals. We call wavelet transform based neural network (WNN). This WNN will combine time frequency power for wavelet transform and the learning power of the neural network. The wavelet will capture harmonic energy at different scale. The neural network will learn to map the patterns to the harmonic frequency. So this will allow us to have real-time dynamic detection under given inverter switching noises. So our input feature must be carefully selected, such as the raw wavelet coefficient and other statistical features like mean variance, cuteness of the wavelet coefficient. And the architecture, we're gonna have the three-phase input signals, a wavelet decomposition that producing a lot of multi-scale coefficient, a multi-layer perceptron, considered as an option for training neural network. We may or may have the CNN layers to extract the local patterns, and finally we have the output predicting the dominant harmonic frequencies. So this is a suggested architecture diagram that we just talked about, we're gonna have two parts, the online and the offline part. And the offline part is the architecture of the WNN that we are talking about. And after we train the WNN, we're gonna put it through the online system to extract the harmonic indices and put it to control and protection application using the input sensor. And inside, we'll have the structure of the multi-layer perceptron network, where we have input layer through some multiple input nodes, put them through some multiple hidden layers and activation function to get us through the output layer, which will be combined with the planned input right there to give us the output for the next layer. So in conclusion, we say that harmonic oscillation remains a very critical threat in modern inverted-based grid, and classical based method would struggle with non-stationary behavior. So we established an AI-driven method, adaptive framework for eliminating the harmonic oscillation. And in the future work, we will try to implement this and include it in the real-world implementation of DSP or FPGA hardware and integrate them, for example, like reinforcement learning into the system so that it can do some automated control also. And we hope that it can do a grid sustainability to provide self-learning, make them extremely well suited for modern power grid with integrated renewable energy and electric vehicles in future. And moving on, we'll focus on more practical application on microgrid and smart grid environment and extend the use of hybrid techniques to boost our adaptability. So here are some of the reference that we use in our paper. This is not the full list, but some of the highlights one. So thank you for listening to my presentation. And if you have any questions, feel free to let me know. Thank you.